Hello, Lovebug. As always, I hope this helps you get to sleep well. Tonight, I am going to talk about the evolution of the steam engines from the pre Dreadnought through the end of the Dreadnought era, covering about from the 1880s to the 1940s. With pre Dreadnought battleships, most of them, pretty much all of them, used reciprocating steam engines. Reciprocating meaning it used a piston and a cylinder, not very much similar to, but the principle was similar to your car, where the steam acted on a piston inside a cylinder to push it up and down to generate, to turn the pressure of the steam into mechanical work, turning the propeller shaft to move the ship. And pretty much, I don't know of any pre-dreadnought battleship that wasn't coal burning for the boilers, and how and why they evolved from coal burning steam turbines to oil, from coal burning reciprocating steam engines to oil burning steam turbines. So starting from the front of the powertrain, where the steam is actually generated in the boilers, coal carried a lot of disadvantages with it. Some advantages of coal were that it produced a lot, like compared to wood, which was a primary fuel source before coal produced a lot more energy per unit of weight, and coal is relatively inert, so it's not really explosive except for certain concentrations of coal dust. So coal, in addition to being the fuel of the ship, coal also had protective value. So the coal bunkers where the coal was stored were actually part of the protective scheme of the ship, and it was estimated that 12 inches of coal were equivalent to about 1 inch of 1890s era quality steel. So the coal bunkers were actually used to help protect the ship from gunfire and torpedoes. Now, some downsides of coal. Starting straight from the coal bunkers, there were a couple of downsides. For one thing, the coal bunkers had to be located very close to the boilers where the coal was burned, because being a solid fuel, coal was not able to be pumped around. It had to be able to be manually carried with wheelbarrows and shovels. Oil didn't have this problem, which is something I'll talk about later. So, in addition to being limited on where the coal bunkers could be, this limited how much bunkerage, the total fuel capacity that a ship could reasonably have, because you couldn't have bunkers 300 feet away from the boiler room, because there was no reasonable way to get coal from faraway bunkers to the boiler room, because the ships burned so much fuel that there was no way that you couldn't design a mechanical system to do that. It would take up too much weight, space, and complexity. But trying to get a crew member to do that, there's no way that crew members with wheelbarrows could move that much coal. The other issue is that by having to have the coal bunkers near the boiler rooms, which are near the central part of the ship, within the armored citadel of the ship, which is prime real estate, you're taking up valuable internal volume for that can't be moved. So that gives you problems with where to put equipment, other things like that. The third issue is that even though the coal bunkers are part of the protective scheme, you have to have a way for the coal to be passed from the bunkers into the boiler room where it can be burned. So you have to have scuttles, coal chutes, watertight doors, things like that. And the problem is that in theory, while the coal bunker should be a part of the ship's protective scheme and therefore help the ship survive a torpedo or shell hit, the problem is that the ship starts to flood and those doors are open. If it's any kind of decent sized hole whatsoever, you're going to have a really hard time closing that door in time, if the door is even adequately watertight to begin with. Because coal, being a very filthy fuel, has a lot of dust, clinkers, things like that, which would interfere with the seal of a watertight door. So even if you were able to close the door and the door was adequately constructed to resist the water pressure, the seal may not be very good, so you would still get leaks through the door into the boiler room proper, which is a very bad thing, obviously. Another issue that coal had was that coal is a very dirty fuel, and because it can't be pumped, it has to be manually loaded. When you'd have to fuel your ship, it could take several days, pretty much everybody on the crew except for the captain and a select few officers, and it would get the entire ship from bow to stern, top to bottom, port to starboard, completely filthy with black coal dust. There was pretty much nowhere on the ship that was safe from getting filthy with it. So coal was not, for its time, it was a good energy source, but relative to later inventions, it was out of date. A couple other issues with coal: when it burns, coal tends to produce very large clouds of black smoke, which in the era before radar, when you were relying purely on visual spotting, even if you were over the horizon from your enemy, if your ship is generating massive clouds of black smoke, they can see you, or you can see them, which is not a good thing. You want to be able to have stealth. And then the final one of the other among many final issues with coal was the actual crew feeding it. Because coal is a solid, there was no way on a ship to provide a machine that would feed it into the furnaces of the boilers. So you had to have firemen or stokers, depending on which navy you were in, what they called them. They were manually feeding the coal into the furnaces. This is a very labor-intensive job, very dirty, bad for your health. Not something that was an enjoyable job. So the firemen were actually paid very, very well relative for their time because of how hard and dirty the work they did was. And because each boiler needed at least one fireman to shovel coal into its furnaces, you need a lot of firemen because early ships, for instance, the USS Texas, which is one of the few surviving World War I ships as built, had 14 boilers, and the boilers were double-ended. So you needed a minimum of, if it, each end of the boilers had 3 furnaces for 6 total, and providing that one fireman could fire all 3 furnaces, you would need a minimum of 28 crewmen at a time just to fire the boilers normally. Then you'd need 3 watches, 3 shifts, so you'd have to have 3 times that number. Plus, in reality, you would need more than 24 men, because at low speeds, when the ship is not generating a lot of power and therefore doesn't need a lot of steam, you don't need as big of a fire. So a single fireman could probably fire all 3 furnaces. But at high speeds, you probably need 3 firemen per side, one per furnace. Because, for instance, on the Olympia that I visited in Philadelphia, at top speed, each fireman would have to be taking a shovel of coal about every 5 to 10 seconds into the boiler, and about a 10-pound shovel full each, which you need a lot of guys to do that. And the other issue being, with a coal-fired ship, typically coal-fired ships can't keep up their maximum speed for very long because the stokers will get tired because they're working in 120-degree conditions, throwing a 10-pound shovel of coal every 5 to 10 seconds. So it was really difficult for a coal-fired ship to keep up top speed for very long because the stokers would get tired. Now, on to the reciprocating engine side of things. Reciprocating engines were reliable and they were relatively fuel efficient, so they were a good power source in their day. But as ship speeds got higher, reciprocating engines tended to be a little bit out of their element. Because a reciprocating engine, when you've got a large reciprocating assembly weighing, dozens of tons that's changing directions several times per second, that is a lot of unbalanced force, a lot of vibration generated into the ship structure. And because the engine is directly tied into the strongest part of the ship structure, that vibration is distributed throughout the ship, which has negative effects on everything else. Also, it really restricts the reliability of the engine at high speeds, because while some reciprocating engine ships were capable of pretty high speeds, just like the stokers couldn't necessarily keep up the flow of coal for that long to keep the fires up enough for high speed, the engines would also not shake themselves to pieces, but the engines would also tend to suffer damage running at high speed for prolonged periods of time. So even though you had a ship that was theoretically capable of 21 to 23 knots at the later end of the reciprocating engine era, in a lot of cases, the ship could only do that for a short period of time. So its real practical top speed was like 17 knots or something like that before engine malfunction and crew fatigue started to become a problem. Now, later ships did come up with some innovations. Towards the end of the pre-dreadnought era, in the early dreadnought era, they did start to have what's called mixed fired boilers, which were where they would primarily feed on coal, but they would also have an oil supply that could be sprayed into the fire to increase the rate the coal burned out or supplement the coal, and that did help. That did help with the crew fatigue. The other thing is that on certain mixed firing ships, particularly the British ones, the British were very concerned about fuel source because they had a worldwide empire. So British mixed fire ships could run at up to 60% power on oil fuel alone. They couldn't do 100% power without coal, but the British mixed firing ships in particular could do up to about 60% of their design power on purely oil. So if you had coal, you could do great, and if you had only oil, you could still get by. So that helped with the crew workload a lot. And then reciprocating engines, they had better balance systems that came up. Better oils were developed. Forced lubrication systems that supplied engine oil under pressure versus gravity feed helped with the reliability. But at the end of the day, there was only so much that you could do because the reciprocating engine is limited in how fast it can spin. At the end of the day, no matter what you do. So in the early dreadnought era, you had turbine driven but coal-fired ships, where you still had the coal-fired boilers, mixed-fired in some applications. But you also had the early generation of direct drive turbines, which I talked about a little bit in the Dreadnought video. But basically, a turbine is like a pinwheel in a box, where the steam flow across the blades spins the blades. The steam is injected through a series of nozzles that act directly on the blades. And there's different, I won't really get into the specifics of impulse versus reaction turbines. But because it's a balanced rotating assembly in a turbine where a reciprocating engine, the highest speed reciprocating ship engines that I can find are around 150 RPM. A turbine rotor can spin in some ships up to about 6,500 RPM. Now, the problem is that the propeller can't spin that fast. Things would break, it would cavitate, it's just physically impossible. But the turbine in the early ships, they had direct drive turbines, and those turbines generated more power with less vibration, and crucially, they were smaller than reciprocating engines. But one of the issues with the early turbines that were direct drive was that because the optimal propeller RPM is significantly lower than the optimal turbine RPM, that means that the turbine would either have to run at an inefficient speed because turbines function best at high speed, or the propeller would have to function at an inefficient speed because propellers function best at low speeds. So what you wound up with the early turbine ships was that at low speeds, they were tremendously more fuel consuming than their reciprocating engined ships, but at high speeds they were actually more efficient, and that was on the early ships. And there was a lot of things that they went into with solutions that they tried. They tried cruising turbines, which help with the efficiency. Basically, the idea is that the main turbines can generate full power for full speed, where you have a smaller cruising turbine of reduced power that uses less energy to run, that can be switched on or off when you're just cruising around at lower speeds and lower power. And that does save fuel, but then the problem is that costs more weight and space, which part of what was so attractive about the turbine to begin with was the fact that it was smaller and lighter than a reciprocating engine. Plus, by the time you got to all the additional pipework, valves, etc., to make multiple, high pressure turbines and low pressure turbines for the main turbines, plus you've got the cruising turbine. Plus, the other thing about turbines is that because of the way that the blades and nozzles are oriented, a turbine can only make itself run in one direction. You need a separate reversing turbine to go astern, where with the reciprocating engine, by adjusting the valve timing, you could reverse a reciprocating engine. But a turbine, you need a second turbine in order to run it backwards. So by the time you got 4 or more turbines on one shaft, it kind of had gotten to the point where it destroyed a lot of the reliability and simplicity that the turbine was originally known for. But nonetheless, the turbine caught on because navies recognized that not only did it give them a higher potential top speed, but by having an engine that could run at full power all the time, it gave them a higher practical top speed as well. One of the other things that happened in the early days of the Dreadnought was oil replaced coal as the fuel of choice. And there's a lot of reasons for this. For one thing, at the end of the day, oil is more energy dense than coal. So for a given weight of fuel, you could have a greater amount of range, greater distance you could sail without needing to refuel. A second really big plus for oil is that with oil, because it's a liquid, you can store it anywhere because it can be pumped. So oil storage tanks didn't necessarily have to be close to the boiler room where they were going to be burned. Oil storage tanks could be pretty much anywhere you wanted them on the ship, and you would just pump the oil in or out as needed, and that was all it had to be. Now, there were a lot of skeptics to oil early on because it was feared that oil was less inert than coal, more flammable, so it would cause the ships to burst into flames if they took a hit. But it turned out that oil actually had better protective quantities than coal did as well. And you got to keep in mind when I talk about this was 100 years ago when nobody cared about the environment. So, just like coal, oil could be used as part of the protective system because by having it in tanks outboard of the vitals of the ship, that oil, that mass of the oil, the liquid mass, would help to prevent explosions from sending shrapnel through the sides of the ship to the important part and flooding the inside part where the people and machinery is. Now, coal, as you used your coal supply, a couple of problems happened. For one thing, your coal that used to be able to absorb energy of a hit was no longer there, so you didn't get that protective effect. For a second thing, as you burn thousands of tons of fuel, your ship rides higher out of the water. And when it comes to a battleship, this is a bad thing. Reason being, the armor belts were designed to sit at a certain designed waterline, designed draft of the ship, in order for the armor to protect the ship most effectively. If the ship is riding too high or too low in the water, the armor may not be where it needs to be to protect the ship, and you're going to suffer worse damage than you have to. Now, coal, as you burn thousands of tons of coal, it's just gone and there's nothing you can do about it. So your ship rides higher than is ideal, and your armor belt, the underside of your armor belt may be exposed. So even though your ship has enough armor, a shot may go under the armor belt because it's out of the water because the ship is floating too high. Now with with oil, when you burned your thousands of tons of fuel, you could, and again, this was in the days before they cared about the environment, you could take on seawater into your empty oil tanks to reballast them, and you would still have the protective effect of the mass of that fuel, and you would be adding weight back to your ship, so the ship would be back in trim, riding back at the level it was designed to ride in the water at. So oil actually turned out to be a pretty good protector. Another real benefit of oil was that because you didn't have to have a guy physically scooping the fuel into the boiler, it could be pumped. So not only could it be transferred from tank to tank around the ship, stored anywhere you wanted, and brought where you needed it, but you had oil sprayers that were spraying oil into the boilers instead of having to have somebody physically shoveling it in. So where before you would need several firemen to operate a boiler, two guys could operate the boiler on an oil-fired ship. One guy managing the burners, basically just adjusting the rate that the oil was being sprayed in at. One guy checking the gauges and adding water when you needed it. So this significantly decreased the number of men needed to run the ship, which was good for payroll costs for the Navy. It was good because a ship that needs a bigger crew needs to be a physically larger ship, which is more expensive. So again, more expensive for the Navy. And because you don't need to be having as much space devoted to housing people to run the engines, more space is available for other things. Another benefit is that by the fact that you didn't need to have giant coal bunkers near the engine rooms in the central protected part of the ship, you could use because the oil tanks could be anywhere, you could use that useful and protected internal volume to do a lot more with it. Oil was just a great upgrade. The only downside in the early years really was that before oil production was really scaled up, it was hard to get in some parts of the world, which is why, of all places, the Royal Navy, England, waited till later than a lot of other people to switch over to oil firing because they knew they could get coal anywhere, but they didn't know about being able to get oil anywhere. Now, as you got into the later part of the 1910s and early 1920s, geared steam turbines began to come out, which were far superior to the direct driving. What geared means is that you have a gearbox, essentially a transmission, but not really like that, but in a way. So the steam turbine is able to operate at its efficient high speed. It runs through a gearbox, which reduces the high speed of the turbine down to the low speed that the propeller shaft operates at. Now, the problem is that the gearing is very expensive, very requires a lot of precision down to about 0.002 of an inch. Long time to make. You need a lot of facilities, a lot of tooling. It's expensive. It's hard to get. It's a long lead time item. So it took a long time, and it's hard to design gearing that can hold thousands of horsepower. So it took a long time for that, even though everybody had known that you want to have the turbine running at a higher RPM and the propeller at a lower one, it took a long time to actually turn that into a practical, usable fact. But around the 1920s, you started seeing geared steam turbines appearing, which were, like I said, you've got a gearbox reducing the speed of the turbine to the speed the propeller needs, which allows both to run at their most optimal RPM. That was a really good thing because now the ships weren't fuel hogs at low speed, but economical at high speed. Turbine ships were still slightly more fuel hungry than a reciprocating engine ship during this period, but they had a lot that they had improved a lot to where it wasn't a huge disadvantage anymore. And by this point, they had come up with what's called cross-compound turbines, which were even more efficient. So basically what that meant is even though you don't have a ton of physical space to have one long turbine, as the steam goes through it and loses its pressure, you have to increase the diameter of the turbine wheels in order to extract the same amount of power. Problem is, on land, you can do that. You can just line up 100 feet of turbine blading if you want, and it gets successively bigger going down the line. But on a warship, they don't have the space for that. So what I think the U.S. Navy were the first to do this. They came up with the cross-compound turbine, where the high-pressure and the low-pressure turbine sat side by side, both of them feeding an input into the reduction gear, both of them driving a common propeller shaft. So the steam went in the high-pressure turbine at full pressure from the boilers and temperature, got used one time through that, then crossed over the low-pressure turbine, where the remaining energy was extracted from the steam before it was completely spent. And in the U.S. Navy, at least, the low-pressure turbine actually developed more power than the high-pressure turbine. So that was a very simplified view of the steam turbines. Now, in the 1920s, the U.S. Navy came up with an interesting idea because they figured out that they wanted ships that were more maneuverable and more powerful than reciprocating engines, but also more fuel efficient than the turbines of the day. In the U.S. Navy, they uniquely came up with, for large ships, what's called the turboelectric drive. And that was a really interesting solution. Basically, the turboelectric drive, you've got the same boilers, but instead of driving the main engines from the boiler steam, they're driving main dynamos, main generators, which are generating massive amounts of electrical energy. And instead of having steam turbines for the engines or reciprocating engines driving the propellers, they had giant electrical motors. And this gave you a lot of advantages because the steam turbines that were driving the generators making the electrical power could operate at the most efficient speed for the turbine, which meant that you got the most bang for your buck in terms of fuel usage. Also, by having, instead of, I say only up to 4 main engines that you would have to individually share the load on, some of them had 8 or more main generators. So this gave you the ability to run only the amount of generators that you needed for the amount of power that you needed at the current moment. So basically, if you were going really slow, you could steam with as little as 1 or 2 generators online, but those 2 generators would be running all 4 electrical motors turning the propellers at low speed. Where if you needed high speed, you would have all the generators online, running all of the propellers at full load. And this gave you some pretty cool advantages. For one thing, because the individual components of the system were smaller, this meant that you could have much greater subdivision, much greater watertight division between the different components of the machinery spaces, so the ship could survive more damage. Basically, you'd have a smaller amount of the ship flooded for any given hit. The other thing is that the propeller shafts were kind of an Achilles heel in the ship, because the propeller shafts, the engine rooms on a ship, even though the engine's on a small boat or at the very back of the ship, on a large ship, the engine room is typically around the middle of the ship, so hundreds of feet from the stern, that you have to have a propeller shaft spinning at high speed. And there were actually some ships that were sunk when something happened to their propeller shafts, because you have a 300-foot long shaft going down the middle of the ship, and if you took a torpedo hit right on the screw that blew off the propeller, that would wreck the propeller shaft, and then the propeller shaft, turning under the force of thousands of horsepower, would flail out of control through all the bulkheads, the walls, and basically open up a flooding path right back to the engine room, which actually sank a few ships. Now, with the fact that you had the electric motors, which could be closer to the stern, you didn't have to have nearly the same length of propeller shafting running down the middle of the ship. This also meant less packaging issues, because you didn't have to have, high pressure, high grade steam piping running for hundreds of feet. You could just run some electrical cables, and obviously they had to be big. But this allowed you to have better subdivision, as well as no propeller shafts that could be a potential vulnerability to the ship running halfway down the length of the ship. Turbo electric drive was for the U.S. Navy. It was more efficient than a steam turbine ship, but it was also more powerful than an equivalent reciprocating engine ship. It was a really, really well designed system. I think it's kind of a shame that it wasn't more pursued with the U.S. Navy, because they only used it for a couple of ships. And the reason that they stopped using it was weight and cost. Basically, in the 1920s and 30s, after World War I, the World War to End All Wars, the major naval powers entered into a series of naval treaties intended to limit the growth of future ships, as well as limit how long you could basically have a building holiday of a certain number of years where you weren't building new ships. Now, the problem was that now, before the war, there had been no limitations. You could build whatever your infrastructure and budget would allow. Now you had a hard upper limit that you were supposed to try and follow. And the problem being, by the time that you have the boilers, electric motors, distribution for all that, electric generators, yada yada, a turboelectric plant was heavier than a steam turbine plant per unit of horsepower. And in the treaty limited era that was the 1920s and 30s, you really couldn't afford, because you were trying to build ships that were faster, more powerful, and better armed than earlier ships with the same displacement roughly. You really didn't have the extra weight to put into the engineering plant. So unfortunately, the turbo electric drive died, which is a shame, because, like I said, I think it was a really great solution, better subdivided, more powerful, and more efficient. But it was just too heavy during the treaty era period to be continued. So while the U.S. Navy did have success with it, ultimately during World War II, they went back to oil-fired steam turbines, because that was relatively efficient and significantly lighter. And while turbines are still precision machinery, a turbine is less expensive to manufacture than a 40,000 horsepower electric motor that's the size of a house. Not to mention the vast quantities of copper wiring that you needed in order to be able to connect everything on an electric ship. So that's kind of a very brief synopsis of the evolution of large ship propulsion plants. Obviously, at a very, very basic level. I really don't know enough to go into a higher level on that. But that's a brief synopsis. Hope it helped you sleep well.